Hello everyone. In this session, we'll discuss about PIC microcontroller. So PIC here is nothing but peripheral interface controller. Now we are going to see one family inside this PIC microcontroller, that is 8-bit microcontroller. So before going to see something about that 8-bit microcontroller, let us see some important issues which are related to this PIC. So the manufacturer of this PIC microcontroller is Microchip. So Microchip is the parent company which is going to design these PIC microcontrollers. Okay, so they have not distributed this architecture to any of the companies or any of the organizations. As if you take the example of 8051, now its architecture has been distributed to many companies. So those companies are designing their own microcontrollers based on 8051 architecture. Okay, but whereas here this the architecture of PIC is only with the Microchip, so they can only design these PIC microcontrollers. The copyright is only for this Microchip. Okay, and if you look at the PIC families here, there are 3 or 4 different variants of this PIC. Okay, like 8-bit microcontrollers, 16-bit, 32-bit, as well as DSP microcontrollers. Okay, so if you can see inside this 8-bit microcontrollers, PIC 10, 12, 14, 16, 17, and 18, these are the series which comes under this 8-bit microcontroller. Okay, family, and the 16-bit microcontroller family has series like 24F and 24H. Okay, and 32-bit will have 32, and DSP processors will have PIC 30 as well as PIC 33F. Okay, so out of these PIC families, we are talking about 8-bit family, and inside this we are going to look about PIC 16 series. Okay, so let us see what is this PIC 16 series. So we are talking about this, that is PIC 16F877a is the controller which we are going to discuss about. Okay, and initially we'll start this microcontroller with its features. So as you can see, here it has totally 35 instructions, single word instructions. I'll talk about this word in the later sessions. Okay, so it has a total of 35 instructions, and most of these instructions will be executed within one single cycle. Okay, except the instructions like jump instructions and loop instructions, they will take more than one cycle. Okay, and the operating speed, that means the frequency that we can apply to this microcontroller is a maximum of 20 megahertz. Okay, and it has 14.3 KB of flash program memory, which is nothing but your core memory, and 368 bytes of data memory, which is nothing but RAM, that is data memory. Okay, and 256 bytes of EEPROM. Okay, this is basically used for storing lookup tables. Okay, and 5 input-output ports like port A, port B, C, D, and E, and it has 3 timers internally. Those are 2 8-bit timers and 1 16-bit timer, and it has 2 CCP modules. Okay, CCP here is nothing but capture, compare, and PWM. Okay, and it has 2 synchronous serial protocols. That is there is one peripheral MSSP, master synchronous serial port, which supports 2 synchronous protocols, that is I2C and SPI, and it has USART, which provides synchronous as well as asynchronous communication, serial communication, and it has PSP parallel slave port. Now this particular port is basically used for connecting some slave devices like 8255, and it has a 10-bit 8-channel ADC. So ADC is basically used for converting analog signal into digital form, and so it provides the output in 10-bit digital form. Okay, and it has 2 comparators, and it has 15 interrupt sources. Okay, power saving modes like idle and power down, and operating voltages ranges between 2 volts to 5.5. Okay, so there are some controllers which runs with 2 volts, and the maximum voltage that they can run with is 5.5 volts. And it has 2 reset sources, power on reset, and the other one is brown out reset. Okay, so let us compare the basic 8051 microcontroller with the series, that is PIC 16F877a. Okay, so if you people are aware of this 8051, then you will come to know why actually we are discussing about this differentiation. So both of them are 8-bit controllers, but now this 8051 is based on CISC architecture, but PIC here is based on RISC architecture. So there are lots of differences between RISC and CISC. So when you go with RISC architecture, it will have less number of instructions, and when you go with the CISC architecture, it will have more number of instructions. And in case of RISC, uh, most of the instructions will perform only single operation, but whereas in case of CISC, most of the instructions will perform multiple operations. So when it comes to the compiler designing, in case of RISC, it is very much complex, and in case of CISC, it is very much simpler. And coming to the hardware implementation, here it is simple in case of RISC, but whereas in case of CISC, it is complex. Okay, so and here in case of RISC, register to register operations can be carried out, but whereas in case of CISC, memory to or memory based operations can also be carried out in case of CISC. Okay, and both of these are Harvard architecture, so it means two separate memory modules are used for code as well as for data memory, and it has 35 instructions and it has 250 instructions. And here one machine cycle is nothing but 4 clock cycles, but whereas here it might be 12, 6 or 1. Okay, if you're talking about the basic 8051 architecture, it supports 12 clock cycles as one single machine cycle. So machine cycle here is nothing but time taken by the processor to execute a single instruction of minimum length. Okay, and as I told you that manufacturer of this particular PIC is only the parent company, that is Microchip, but whereas coming to here, as the Intel have distributed its architecture to many organizations, so they can implement, so they can design their own microcontrollers based on this particular architecture. Okay, and here it consumes low power as compared to 8051, and it consumes high power as compared to PIC. It comes with many peripherals, that is PIC, but whereas the 8051 comes with only few peripherals, and it is low cost and it is high cost, and it is basically used in industrial applications, that is PIC, and 8051 is used in low-end applications. Now let us see the pin structure of this PIC16F877a. As you can see, it is a 40-pin IC package. Okay, and it has totally 5 ports. As you can see here, RA0 to RA5. Now these pins indicate port A, and RA0 to RA2, these are port E, and RC0, RC3 here, and the remaining pins are here. RC4 to RC7, these are port C, and RD0, RD1, D2, D3, 4 to 7, these are port D, and RB0 to RB7, these are port D. Okay, and here you can see that each of the pin, most of these pins are going to provide multiple functions. Okay, so depending upon our requirement, we are going to select one particular functionality of these pins. Okay, but when you are programming this controller, we are going to use 5 pins. Okay, out of these 40 pins, as you can see, VPP, PGD, PGC, PGM, and then a ground. Okay, so these are the 5 pins which are used while programming this controller. Okay, so VPP is a supply voltage, that is programming voltage, and the PGD is a data pin, and then this is a clock pin, and this is the mode pin, which indicates whether you are going to program the controller or not. Okay. So as I told you, it has totally 5 ports: port A, port B, port C, port D, and port E. Okay, as you can see, each of these ports will have some pins, like port A is having 6 pins, port B is having 8 pins, C and D also have 8 pins, and port E is having 3 pins. Okay, a total of 33 GPIOs. Okay, now each of these pins are designated with the name or with the symbol R. Okay, so RA0 indicates port is 0th pin, and RA5 indicates port is 5th pin. Okay, so in the same way for port B, that is RB0 to RB7, RC0 to RC7, RD0 to RD7, and RE0 to RE7. Okay, and all of these are bit addressable. So it means I can directly use this name in my embedded C program. Okay, like RA0 equals to 1. Right? Let us see all those things. Now, in order to use those particular ports, okay, so we have to access some registers. Okay, now coming to the registers, here tris as well as port, these registers are common for all the ports. Okay, so these are common, and apart from these registers, we'll also use some other registers. Okay, so we'll see what is this tris and what is this port register. So tris register is basically used for selecting the direction of the port, whether it has to be used as input or whether it has to be used as output. Now that is decided with the help of this tris register. Okay, and port register is basically used for holding the data while transmitting to the uh, external world or while receiving from the external world. Okay, so here tris A is a register which is used for selecting the direction of this port A. Okay, now if you program any of these tris A register bits to logic 0, it means the respective pin is now acting as output. Okay, if any of these tris A register bits are programmed to 1, then it means the respective pin is now acting as input. Okay, so 0 for output, 1 for input, similar to the case of 8051. Okay, and port A, this is the register which is going to hold the data while transmitting or else while receiving from the external world. Okay, and apart from these two registers, as I told you that we need to use some other registers. Okay, and this is not mandatory for all the ports. Okay, only some of the ports will be using other than these two registers some other registers like ADCON1, which is analog to digital control register. Okay, now why do we use this particular register in case of this port A? Because by default when you turn on the controller, all the port A pins as well as port E pins, port A and port E will be acting as analog inputs. Okay, they will not be acting as GPIOs, now they will be acting as analog inputs. So before using this port A or port E, you have to configure those pins to work as GPIOs. Okay, now that is done with the help of this ADCON register. Okay, now out of these 8 bits, we'll be using only these 4 bits. Okay, in case of GPIOs, that is PCFG0 to PCFG3. These are called as port configuration pins or port configuration bits. Okay, so anything like 0, 1, 1, X. Okay, so if you write 6 or 7 into these bits, okay, then port A and port E will be working as GPIOs. Okay, other than those two values, the port A and port E will be working as analog inputs. Okay, so if you want to use port A or port E as GPIO, then you have to configure this ADCON1 to 0x07. Okay, 7 or 0x06. Okay, 6 here is nothing but 0, 1, 1 and 0. 7 is nothing but 0, 1, 1 and 1. Okay, so this configuration will make port A and port E to act as GPIOs, not as analog inputs. Okay, so tris A for selecting the direction, port A for holding the data. Then the same way if you take port B, so port B has totally 8 pins. So tris B is used for selecting the direction and port B is the register which is used for holding the data. Okay, and for port C, tris C and then port C. Okay, and for port D again the same, tris D for selecting the direction and port D for holding the data. And for port E, apart from these registers, you have to use one more register, that is now ADCON again. Okay, so tris E for selecting the direction and port E for holding the data, and ADCON is used for configuring this port E to act as GPIOs. Okay, so let us take one example here. I want to interface this LCD to this port pins. Okay, let us see how to interface this. Now it is a 16-pin LCD. Okay, so it has a ground VCC for supply, V for contrast control, and RS pin, which is nothing but register select. Now this LCD can accept commands as well as data. Okay, so data will be displayed on the screen on the LCD and based on commands. Okay, so data will be displayed on this particular LCD screen based on the commands. Okay, so if you want to send command to this LCD, then this register select should be programmed to 0. Okay, if you want to send data, okay, then this should be programmed to 1. It means you have to send logic 0 or logic 1 through this particular pin. If you are sending logic 0, then LCD treats the incoming information as command. Okay, if you are sending logic 1, then LCD treats the incoming information as data. Okay, and then read write. Now whether you want to read the information from the LCD or write the information to the LCD. Okay, so sending a logic 0 through this pin will tell the LCD that now the data should be returned to the LCD. Okay, and logic 1 will tell the LCD that now the controller wants to read the data from the LCD. Okay, and enable. So this signal or this pin should take a transition from logic high to logic low whenever we want to write the data. Okay, so after placing the data onto this data pins, these are the data pins. Okay, So we'll place the data onto these data pins. Then there should be a transition from logic high to logic low on this particular pin, so that this information will be latched onto the LCD. Okay, and if you want to read the data, then there should be a transition from logic 0 to logic high on this particular pin. Okay, so if you want to write the data, then there should be one transition of logic high to logic low pulse on this particular enable pin after placing the data onto these data pins. Okay, and then LED and LED plus and LED minus, these are used for backlight display. Okay, so if you want to connect, or if you want to interface this particular LCD to this PIC microcontroller, how many signals we require? First of all, let us see how many signals or how many pins we require. So here DB0 to DB7, these are the data pins. So a total of 8 data pins are required. Okay, and apart from these 8 data pins, we also require some control signals like RS, RW, and enable. Okay, so a total of 11 signals are required here, or 11 pins are required from the microcontroller end. Okay, now these are the commands, okay, which we are going to use. Okay, so if I send the command something like 1, now it will clear the display. If I send something like the command 2, so the cursor will be returned to the first position. Okay, so out of all these commands, we'll be using some commands in most of the applications like 38. Okay, so 38 is a command which makes LCD to work in 2 rows, and that is 2 rows of LCD are activated or enabled, and each and every character is represented with 5x7 matrix. Okay, so we use 38 as well as we use 80. Now this 80 command will force the cursor to point to the starting point. Okay, and if you want from the second position, then you have to use 81. Okay, and you have one more command like C0, as you can see. So if you want to start, if you want to display the data from the second row first position, then you have to use this C0 command. Okay, so basically we use 38, 80, and then 0E. Now this is display on cursor blinking, and then we can use this clear display. Okay, so what I'm going to do here is I'm going to connect this DB0 to DB7 to any one of the port pins, okay, which has 8 port pins, and then I'm going to connect this RS, RW, and enable to port E. Why? Because port E is having only 3 pins. Okay, so this is how I'm going to connect 11 pins of the controller to the 11 pins of this LCD. So let us see how to write embedded C program for this. Okay, so let us see the procedure. So if I want to send a command, then what I have to do? Okay, so to send a command on the LCD, a particular command is first specified on the data pins with RW equal to 0. Why? Because we are writing some data to the LCD. Okay, now that information is command. We are treating it as command. So definitely I have to program this RS to 0. Okay, which tells the LCD that now the incoming information is command. Okay, and a high to low pulse is given at enable pin when data is sent. Okay, so you have to place information onto the data pins, and then you have to send logic 0 through this RW pin, and then logic 0 through this RS pin, and there should be one high to low transition on this enable pin. Okay, now this makes this command to be stored inside the or this command is going to command the LCD to do a particular task. Okay, and then if you want to send data, you have to carry on the same thing, but after placing the information onto the data pins. Okay, so we have to send RW to 0. Okay, and then RS should be this time 1. So we have to send the logic 1 through this RS pin. Okay, and then a logic high to logic low transition on this enable pin, which makes the data to be written onto the LCD. Okay, now let us see how to write this. So I have included one header file like #include pic.h. Okay, so this header file is going to include all the registers. So I can use all the registers which are present inside this header file. Okay, and then I'm defining RS, RW, and enable with some port pins. Okay, like RE0, RE1, and RE2. So instead of using RE0, RE1, and RE2 in my program, I'm going to use RS, RW, and then enable. These are macros. Okay. Now, wherever you use RS, RW, and enable, those are replaced with RE0, RE1, and then RE2. Okay. So I'm taking one global variable like int I. Okay. And I'm using 2 functions here. One is my data function, which places data onto the data pins, and the other one is command function. Now this places command onto the data pins. Okay. Now let us see the main function first. So this is my main function. So I'm using one local variable int I. Now here my character or my string is citrus. I want to display this citrus on this LCD. Okay. So initially what I'm doing here is I'm using port E as well as port C. So as port C is having 8 port pins, okay, so I'm using those port C as data pins. Okay, so initially I have to configure this port C by using tris C. Okay, now they are acting as output, so that's the reason I'm making this tris C to 0x00. Now all the bits inside this tris C are written with 0. It means all the port pins of port C are now acting as output pins. Okay, and as I'm using tris E, so definitely I have to configure this tris E to GPIO. For that I have to use adcon1. Now it is written with 0x07. Okay, I can go with 0x07 or else I can go with 0x06. Okay, which makes this port E to act as GPIO. Okay, and then I'm using tris E because all these control signals are output signals which are coming out of the controller and received by the LCD. So that's the reason I'm making again them to 0x00. Okay, now what I have to do initially, I have to tell the LCD what actually the LCD has to do after getting the data. Okay, it has to display the data from the first position. Okay, so that's the reason I'm sending the command first, that is LCD underscore command 0x38. Now this command makes the LCD to enable 2 rows of the LCD, and then each and every character is represented with 5x7 matrix. Okay, and then I'm sending the next command, that is 0x80, which makes the cursor to point from the starting position. Okay, and then LCD underscore command 0x0e, so I'm sending 0x0e, which makes display on cursor blinking, and then I'm clearing the display. Okay, if you have some data which is already displayed on the LCD, now that gets erased, okay, with this particular command. Okay, after that I'm sending each and every single character, okay, from this array, okay, to the data function. Now let us see how these command and data functions are implemented. So as I'm sending some characters, okay, so if you look at this command function, it receives this character. Now that character is placed on port C. Why? Because now port C is connected to data pins of LCD. Okay, so this character, that means command is now placed on port C. Okay, and as I have to program RS to 0, so RS to be programmed to with 0, and RW is again 0, and there should be one high to low transition on this enable pin. Okay, this makes whatever the information present on this port C to be latched onto LCD. Okay, in the same way I have implemented the data function, where you can see initially I'm placing this data onto port C, and then I'm selecting this time the data register. Okay, if RS is 1, it means data register is selected. Okay, and then RW is 0, so it means I'm writing the data, and then a high to low transition on this enable pin, which makes whatever the information present on these port C lines is now again latched onto the LCD. Okay, so this is how you're going to use GPIOs for interfacing any kind of devices. Okay, thank you.